We have growth. There are three large crystals varying in shape from round to geometric. This literally happened overnight because last night the vial was all solution and no crystals. The reason for me thinking there was no prior growth was because although I have uncovered the chem-wipe covering to only be one layer, the solution has evaporated about halfway. The lack of crystal growth can be due to the placement of the vial. Currently it resides on the radiator. The added heat may have caused the solubility to change for this molecular solid because as temperature increases, so does the solubility constant. For example, we originally used 25 degrees Celsius or 77 degrees Fahrenheit and a solubility constant of 1.41 grams per 10 milliliter water for our calculations. If the heater reaches 30 degrees Celsius or 86 degrees Fahrenheit, then the solubility constant will change to 1.66 grams per 10 milliliter water, making our original calculations incorrect for making a saturated solution at that temperature. However, the added heat also increased the rate of evaporation. With the solution evaporating more rapidly, the concentration of alum should increase, thus allowing the solution to stay saturated. The heat should not affect the solution and alum grows significantly, as the rapid rate of evaporation helps to counteract the higher solubility constant. To calculate the percent yield, we first have to find the limiting reactant in all four reaction steps. In the first reaction, we started with 1 gram of solid aluminum foil, and after we weighed the filtration paper with the impurities from the first step of the experiment, we found that we actually only had 0.88 grams of aluminum. We also had 0.2 moles of OH minus, and water was in excess. We wanted to find the moles of the AlOH4 minus. So, using stoichiometric relationships, we found that aluminum was the limiting reactant, yielding 0.0326 moles of AlOH4 minus. We used a similar procedure for the second reaction. We saw that we had 0.0326 moles of AlOH4 minus, which we carried over from the last calculation. We also saw that we had 0.1125 mole of H2SO4, which we got from using 12.5 milliliters, which is half of the required 25 milliliters from the procedure, times 9 molar. We wanted to find how many moles of AlOH3 there are. So, using stoichiometric relationships, we saw that AlOH4 minus is a limiting reactant, and it yields 0.0326 moles of AlOH3. For the third reaction, we again used stoichiometric relationships to determine the limiting reactant. We carried over 0.0326 moles of AlOH3 from the previous calculation. We also determined that there was 0.1575 mole of H2SO4, which comes from the remainder of the 25 milliliters of H2SO4, or the 12.5 milliliters. However, we also had to add an extra 5 milliliters because the precipitate was not dissolving completely and we needed the reaction to complete all the way. Using the stoichiometric relationship, we determined that AlOH3 is a limiting reactant and it yielded 0.0326 moles of Al3+. Finally, we were able to determine the theoretical yield of alum using the final reaction. Looking for the limiting reactant, we used 0.2 mole of K+, which was determined from the first reaction. We also used 0.0326 mole of Al3+, which was carried over from the previous calculation. We also found that there were 0.27 mole of SO4 2- total using the 30 total milliliters of 9 molar H2SO4. The water was in excess. Using stoichiometric relationships, we determined that the Al3+ is the limiting reactant and it yielded 0.0326 mole of alum. The theoretical yield of alum was determined to be 0.0326 mole. Using all of this information, we are now able to calculate the percent yield of the experiment. We found that there were 15.5 grams of the theoretical yield of alum. Experimentally, we found that there were 16.2 grams of alum. Using this and the percent yield equation, we saw that there was a 104.5% yield. Our percent yield was above 100%. This means that we made more product than the reactants theoretically could yield. This may have occurred in an early reaction. In the first reaction, we dissolved aluminum foil and potassium hydroxide. We then used the vacuum filtration technique to filter out any impurities the common everyday solid aluminum may have contained. We only completed this step once. Without repetition of the vacuum filtering, we may have not filtered out all of the impurities. This could have been carried out throughout the remainder of the reactions and added more mass to the final alum product. Another source of error could have occurred after the alum was synthesized in the final reaction. We needed to wash the alum using a 50-50 water ethanol solution in a vacuum filtration setup. While we did wash the alum and filter impurities from it a total of 3 times, the alum product itself may have not been dry all the way. While precautions were taken to avoid this step, such as using the quick-drying ethanol solution rather than pure DI water and leaving the alum powder on the filter paper until deemed fully dry by my lab partner and I, the alum powder still might have not been fully dried.